Hello and welcome to today's lesson where we're going to look at the properties of half-life, which is part of the atomic structure topic in GCSE Separate Science physics. So in today's lesson we're going to try and understand what the half-life of a radioactive substance is and how it then links to the properties of that particular radioisotope. So if we're successful and learn in today's lesson, we should be able to understand and define what half-life is, understand how you can work out half-life of a radioactive substance, and finally determine the dangers of radioactive substances due to their half-life. So in today's lesson we'll be looking at the following part of the GCSE Separate Science physics specification, half-lives and the random nature of radioactive decay. Now the half-life of a radioisotope is a fixed value due to the random and spontaneous nature of the decay. So each radioisotope has a measurable half-life which we've determined from experimentation. Now in the previous parts of lessons we've looked at ways in which the half-life of a radioisotope can be calculated. Now it's important to note that half-life is fixed as each unstable nucleus in a particular sample has the same unchanging chance of decaying and becoming stable. Now we can measure half-life with the same methodology as we've looked at in previous experiments. Now as you can see in the following information, half-lives of radioactive isotopes or radioisotopes can vary between years, months, days, minutes and seconds depending on the radioisotope. So therefore something like uranium-238 has a half-life of 4.5 times 10 to the 9 years, so the radioactive nuclei in uranium-238 do not decay very quickly, whilst something like polonium-214 has a half-life of 1.5 times 10 to the minus 4 seconds. So this tells us that polonium's nuclei are very unstable and will decay extremely quickly. Now the half-life of a radioisotope can never be varied. We can only account for it and never change it. So there is no way for us to change the value of half-life for any radioisotope in the universe. So this means the half-life of a radioisotope is constant. Now although in reality in the measurements when you have an experimentation there will always be a slight variance in the half-life values due to the random nature of radioactive decay. Now, remember, just to clarify a key point people have a misconception on, half-life is not the time for the isotope to lose all of its activity. Rather, it is to half the activity. So isotopes stay radioactive for a lot longer than their half-lives. So for example, if we look at this table and we see iodine-131 has a half-life of 8.1 days. Well, it's very tempting to say that after 8.1 days, iodine is no longer radioactive. That's not the case. That's not true. After 8.1 days, the activity of iodine has decreased by 50%. It's gone down by half, but it is still radioactive. Now, different half-lives of isotopes makes them suitable for different roles in the world. And this is also very important, and it links into the type of radiation emitted by the nuclei, as this will also determine their function in the real world. So for example, cobalt-60 is used for cancer therapy and has a half-life of 5 years, because that means we do not have to replace the cobalt in our radiotherapy machines very often. Whilst we might want to use something like technetium for brain scans, which is 6 hours, because it has a very short half-life, so therefore it will not stay in the body for very long if we inject it into a human body. Same for iodine-123. So you can see that it is important to note that the length of the half-life indicates the suitability for the function of that particular radioisotope. And in addition, the type of radiation can be a factor. So for example, in brain scans, in cancer therapy, in thyroid therapy, it's very important that the emission from the unstable nuclei is gamma radiation, as that's the only type of radiation that can get into and out of a human body. Now there are many isotopes with long half-lives in our universe. Things like calcium-48, selenium-92, potassium-40, which is the radioisotope found in foods, uranium-235, which is the radioisotope found in nuclear power stations, and plutonium-244, which is the radioisotope found in nuclear warheads. Now, Importantly, we've got to think of the following question. Why is a radioisotope with a long half-life dangerous? Well, a long half-life indicates that the isotope will be radioactive and emit a lot of radiation for a long period of time. So this means the radioactive isotopes could cause ionization over a long period of time. So it's important to note that if a radioisotope has a long half-life, then its level of danger and activity will remain constant for a long time. So this means that the risk associated with long half-life isotopes does not decrease by much in a human's lifetime. So the activity and the risk of a radioisotope with a long half-life stays relatively constant over a long period of time. Now this can be dangerous because nearby areas will be therefore exposed to radiation for many years. Now on the other side of things, there are many isotopes with short half-lives. So hydrogen 5, iodine 132, which is used in medical tracers, boron 16, beryllium 8, phosphorus 32. Now, why is a radioisotope with a short half-life dangerous? Now, a short half-life indicates that whilst the isotope will not be radioactive for a long period of time, for a short time, the intensity of radioactive emissions will be very high. So this means that for the time they are emitted, the radioactive emissions have a higher chance of causing ionization. So, a radioisotope with a short half-life means that the level of danger it presents to a human drops dramatically over time. So this means that for the time they are emitted, the radioactive isotopes do have a higher chance of causing ionization because they're emitted with a very high intensity. But it also means that the risk of a short half-life isotope will decrease by a large amount over a human's lifetime. So it means that the radioisotope with a short half-life will emit a high amount of radiation at the start of the decay process, but will very quickly become safe. So let's just recap what we've learned so far. Different radioisotopes have different half-lives. A long half-life means the radioisotope is radioactive for a long period of time. This means the risk doesn't change much in a human lifetime. So therefore, a long half-life radioisotope has a constant level of risk and activity in a human's life, which is very dangerous. Now, if something has a long half-life, it means that most of its radioactive nuclei do not decay for a long period of time. Now, a short half-life means the isotope has a high initial intensity and activity of radioactive emission, which is also very dangerous. However, the activity and the risk decrease greatly in a human's lifetime. Now, a radioisotope will have a short half-life if the radioactive nuclei in the sample are very unstable and will decay. So it's very important that you understand the dangers associated with a long half-life radioisotope and the dangers associated with a short half-life radioisotope and how these levels of dangers and risk change over a human's lifetime. So let's just summarize some concepts on radioactive decay and half-life. Radioactive decay is random, and the half-life of a radioactive isotope is the time it takes for the number of nuclei of the isotope in a sample to half, or the time it takes for the count rate or activity from a sample containing the isotope to fall to half its initial level. Now, you should be able to explain the concept of half-life and how it's related to the random nature of radioactive decay, and you should be able to determine the half-life of a radioactive isotope from given information. So if you've been successful and learnt in today's lesson, you should be able to understand and define what half-life is, work out the half-life of a radioactive isotope, and finally determine the dangers of radioactive substances due to their half-life. So I hope you've enjoyed today's lesson on the properties of half-life, which is part of the atomic structure topic in GCSE Separate Science Physics. Thank you very much for listening to today's lesson, and have a lovely day.